say something. So it's really a great pleasure to introduce Dima, as we tend to call him. And Professor Durayev's work falls in the area of dynamical systems and has particular focus on the problems of homoclinic behavior and dynamical problems related to physics. Dima is very prolific. He has over 100 published papers, and his work is very much appreciated by experts. Indeed, very importantly, Dima gave an invited talk at the International Congress of Mathematicians in Hyderabad in 2010. Possibly this is one of the most prestigious talks one can give in mathematics, and certainly confirms a strong recognition by people in the subject. And Professor Durayev's work is also increasingly well cited. As I mentioned, Professor Durayev's work mainly focuses on homoclinic behavior. In a broad sense, his work covers papers on chaos in the Gunzburg-Landau PDE, on billiards, and also chaos in systems of smooth dynamical systems. His work is original, and it doesn't really fit into that of one particular school. He solved many problems going back to Bunimovic and Sinai, but also problems related to the Brazilian French school of dynamical systems in the context of Pales, Bonatti, and Couverger. Some examples. With collaborator Sergei Zelek from Surrey, he worked on an analytical proof of space-time chaos in the Ginzburg-Landau equations, and this was published in 2010. In this paper, the authors are able to show that the localized chaotic structures in such equations do not cancel out in spite of diffusive effect. And there's a lot of technical issues being resolved in that problem, and the problem of chaos in PDEs is a big problem. Together with Konchenko and Shilnikov, and so Dima comes from the famous school of Leonid Shilnikov in Nizhny Novgorod, he published an influential paper on the dynamical properties of multidimensional diffeomorphism with Newhouse regions in 2008. This paper is about diffeomorphisms in a Newhouse domain, and this is a special domain where we have very complicated dynamics with infinite amounts of attractors. This paper sharpens the Newhouse results, showing that there exists a dense set within a certain region of maps in which certain multipliers are as prescribed necessary. So it's really a significant increase on classical results in dynamical systems by Sheldon Newhouse, which was of the early 70s. Then to emphasize another collaborators which he works with is with Vasily Geldrai from Borek and Rom Kedar from the Weizmann Institute in Israel. He's been working on Fermi acceleration and adiabatic invariance for non-autonomous billiards. And this was a paper published in 2012, and there's ongoing work in this direction. And the problem is about a billiard with moving boundaries and many balls, and it aims to settle the long-standing question whether energy can be transferred to the ball's polynomial exponentially fast. So where we have increase in energy, and that's the Fermi acceleration. So Dima is flourishing at Imperial College, and he's having a major impact. This is evidenced by the large number of excellent papers that he publishes since moving to Imperial, but also by the leadership role he plays at Imperial during local seminars, discussions, but also nationally and internationally. He has been instrumental in building and maintaining high-quality scientific partnerships with national institutions like University of Warwick and Surrey, but also institutions in Russia, Japan, Brazil, and France. I would say he also interacts without boundaries locally with colleagues, as well as almost all dynamical systems PhD students. Okay, so apart from these formal observations, let me say some personal words. I met Dima first properly when he attended a meeting on Hamiltonian dynamics that I organized at the Imperial College in 2002. His attendance was linked to the context that I established with his colleague Sergei Konchenko in 1999, when I decided to make some excursions into homoclinic bifurcation theory myself. Konchenko sent me the Nizhny Novgorod recent PhD graduate Oleg Stenkin, and stories about him could take an entire afternoon, so I will not dwell on those. And Dima's attendance in 2002 arose when Oleg Stenkin was already at Imperial. So the dynamical systems group, which had been started at Imperial by myself and Stefano Lusato in 2000, was given the opportunity to expand. And I was excited to be contacted by Dima in 2006, inquiring about the opening. It was a very exciting opportunity, and Dima was hired in 2007 and started to work at Imperial in 2008, now more than 8 years ago. Dima has been a cornerstone of our dynamical systems group ever since. His working style could be considered unconventional. Few of our colleagues, officers, are without any books or paperwork, but it is very inspiring and stimulating at the same time. Dima's understanding of mathematics and physics extends well beyond his track record, and we all benefit hugely from this in our group. I'm personally glad to see that, despite of all the several challenges to live in London with his family, Dima has flourished scientifically at Imperial, witnessed, for instance, by his citation record and international visibility and presence. I'm personally delighted that Dima is not only a colleague, but also a very good friend. So I hope that we will enjoy Dima's lecture. Thank you.
Thank you. Can somebody switch a microphone? Okay, it works. Microphone works. Great. So this is the title, and okay, so that's where we are. It's kind of a recollection from what I think everybody studied this in school, and this is the picture of classical mechanics, and which says us that the world consists of particles, many different particles, and they somehow move, and they interact. And how they move and how they interact is described by 3 laws by Newton, first and second and third. And even when I first saw this, when I was a schoolboy, when I first saw these laws, it was kind of difficult to agree. Why? No, I didn't mean to agree, but the logical structure of that is not obvious, because you see, the first law basically says that there are some coordinates, so you can choose the coordinates in space such that the second law is correct in these coordinates. And the second law is mass times acceleration equal force, and at least force and what is force and what is mass is not. It's one need a definition for that. And so the question is, should one look at this law as a definition of mass, or maybe a definition of force? So what is the status? What does it actually mean? And there is also the third law, which says something about forces, action equal reaction. But so the forces are not arbitrary, they somehow related to each other. And the question is, there should be, for sure, there should be other relations. Why this particular relation is a part of these very important laws? Why not other relations? So, and these questions are not easy, at least to me. So I actually don't know what. Okay, but what is? There is a way to bypass it. So not to just, instead of really looking carefully what is really meant by them, one should notice that at least we know what acceleration is. Okay, what is acceleration? So if you have a particle, it has a coordinate. Particle moves, so coordinate changes in time. So coordinate is a function of time. You can differentiate it with respect to time. So you will get velocity of the particle. And velocity is again function of time. You can again differentiate it with respect to time. You get acceleration. Acceleration is second derivative of this function, x of t. So then we say that this second derivative of this function is force divided to mass. And whatever it is, so we don't need definition of force and mass, whatever it is, it's kind of, it's somehow some function of coordinates and positions of velocities of all particles. With this point of view on the Newton law, it's just to say that the coordinates of the particles, they satisfy certain differential equations. Okay? There is certain relations between coordinates, positions, and velocities. So, okay. Coordinates of the particles, there is certain relation between derivatives of these functions of time. And relations between derivatives are called differential equations. And this is actually a very important statement. Why? Because it allows us, instead of, okay, so we want to understand the world. We want to understand how particles move, so we can just record coordinates as a function of time. this would be not physics, it would be history. Okay, we just record what happens before. Okay? But now we can do something else. So with this observation, instead of recording all these functions of time, we can try to figure out which this function f, which differential equation our coordinates satisfy. And there is a theorem that if you have differential equation under some mild condition, if you know initial condition, then you know the solution for all time. So the whole information, instead of instead of looking at functions of time, we look at differential equations to which these functions satisfy. And this is a huge shift of point of view, a huge difference in point of views on the same subject. What's important for me in this lecture, so that's what, to my opinion, what physicists study. They study differential solutions of differential equations which emerge in mechanics or in physics in general. And what's important, if you look at this is not an arbitrary differential equation. For example, it's second order. You see it's equation for second derivative, not just for first. And there is also certain relations. You see, for example, the forces acting on a particle are sums of forces from different particles. Also, this action equal react. So these right-hand sides, these functions are not arbitrary at all. And it was not due to Newton, it was due to Lagrange and Hamilton, who finally realized that one of the ways to express all these restrictions on possible right-hand sides is just to say that our system of differential equations have a Hamiltonian structure, what is now called Hamiltonian structure. The structure is, it really doesn't matter what it means. What it means is that, you see, we have, for example, we have n particles and coordinates and velocities, so we have 2n equations, 2n differential equations. And in principle, we could have 2n different functions in the right-hand sides, and the Hamilton principle says no. There is only one function, which is called Hamilton function, such that all these right-hand sides can be obtained by just differentiation from this function. Okay? So instead of 2n function, our differential equations are described by one function. And this function is called energy of the system. It's Hamilton function or energy of the system. And actually, when people say that energy is conserved, there is a law of conservation of energy. Main meaning of this is that, in fact, the equations which govern the system are Hamiltonian, have exactly this structure. And this is, I think, it's one of the major beliefs of the physics that, or axioms of the physics, that if you consider isolated systems, which means that energy is conserved, so no exchange of energy with the outside, or no exchange at all, then on a fundamental level, if it's not a phenomenological description, if it's really, if you think that it's a true description of what's going on, then the description would be given by system differential equation with this additional structure. Okay? And of course, now we know it's not, this was the beginning of 19th century, and now we know that the world is more complicated than that, it's described by quantum mechanics, not by classical mechanics. For example, all particles are, okay, in some sense, all particles are identical, and actually equations are not ordinary differential equations, partial differential equations. Still, this Hamiltonian principle is still true. So even in quantum mechanics, the differential equation has this special structure, Hamiltonian structure in some sense. But we are not touching quantum mechanics in this lecture at all. In the beginning of 19th century, for us, the world consists of particles, and their motion is described by some Hamiltonian equation. And then the equation is, okay, so now we have equation which describe the world. Now let us try to solve it. And it's well known that they are, in general, unsolvable. Okay, the solution exists, but there is no hope to obtain some formulas for that. So instead of solving these equations, we try to draw the solutions, to draw the graphs of the solutions, to analyze solutions. And so what we actually do, we have this function. X is the coordinates of all so-called phase space. Each point in the phase space is, its coordinates are coordinates of all particles involved and all momenta involved. So it's a high-dimensional space, or maybe not so high, it depends on how many particles we have in our system. And this point, when time changes, the position of this point changes. So this point, when time changes, draws us some curve. And okay, we look at this curve. And there are many curves. It depends where you start. You start at this point, you have one curve. Start at this point, you have a different curve. And these curves are really complicated, usually. So there is a tool which is called Poincaré map, which allows a little bit simplify this. So what we do, we take certain surface in our space, and instead of looking at the curve in the solution of our differential equation, we look at intersection with this section, surface. And so we take the first point of intersection, this will be the next point of intersection, this will be the next. And the next point of intersection is determined by our differential equation. So it's a function of previous point. So in this cross-section, we have a function, this pair of function f and g, such that we start at point xp, we apply this pair of function, we get new point of intersection. We apply the same pair of function to this new point, we get the next point, and so on. So we have a certain map, or instead of saying pair of functions, we say map. We have a map on a cross-section, and we iterate this map. We do it many, many times, and we see what happens. And by iteration of this map's point will jump. And for general system of differential equations, we will have arbitrary map, or better say arbitrary diffeomorphism, but I will say map. And for Hamiltonian system, our map will have certain additional properties because Hamiltonian systems are special. So the Poincare maps are also special. This property is called symplectic. Again, it absolutely doesn't matter what does it mean. It's just some relation between derivatives of the map. It's some restriction of the structure. We will not consider all the maps. We consider symplectic maps. And if we believe that the world is described by Hamiltonian equation, then when we do records of trajectories, we of course do it in discrete times. So some event happened, for example, the arrow of our clock just moved, so we just record the position and coordinates velocities. Then next time we make a next record, next time make next record. So we actually have a map, and this map is symplectic. So it's again general claim, general belief that whatever we observe, it's actually a trajectory or obtained by iteration of some symplectic map. So if we want to understand fundamental dynamics of isolated systems, it's what we have to understand. Okay, good. So now what can be said about that? And this is, I don't know if you can see, this is a typical picture of what will happen if you take a symplectic map. For example, this map is symplectic, it's so-called standard map, but doesn't matter. It's very simple situation, and my cross-section is now two-dimensional. So it's very, very low-dimensional system. In high dimension, probably the structure is the same, it's just hard to do. But in low dimension, we can just take a computer, you program for a few minutes, compute for a few seconds, and you get this picture. What you do? You take a point and give certain color to this point. For example, this is supposed to be green, okay? And then you start to iterate, all the iteration will have the same color. Then you take another point with a different color, again put all the iteration. And this is a picture. So you see different colors corresponds to different iterations of different points. The same color corresponds to iterations of the same point. So if I start with the green point here, for example, you iterate, and you wait again for several seconds. You have several millions of iterations, so people compute up to billions of iterations. And what you will see that this, if you start somewhere here, this green, you will see the large set which becomes green. So this green point actually behaves chaotically. Chaotically means that you start at some point, it somehow moves, then it returns close to where you start, and then it moves in a different way. Then it returns again where it starts, and again it moves in a different way, and so on. So it really don't repeat itself. And at the end, the images of this point will give you a very large set, which is called chaotic C, by the person who first drew these pictures, in somewhere in the 60s. And you can take another point. I don't know, so you probably don't see it. On my screen, you will see that there are 3 blue points. And they actually give you the same C, okay? So there are many points which give you chaotic behavior, and this chaotic behavior is large enough. And if you take, for example, this red point or orange, whatever, the behavior will not be chaotic, you see? So it just, the picture is periodic, so it's actually start here and then you go back. So you move along certain curves, Kolmogorov-Arnold-Moser curves, and the behavior will be quasi-periodic. It will be very, very regular, and you will stay here. So for some colors, for example, for this yellow color, you have regular behavior. For some colors, you have chaotic behavior. And this is what happens. It really doesn't matter which symplectic map you take. It's important it's symplectic, but which map, it doesn't matter. What you see is chaotic C and stability islands. So this is island of stability. This is chaotic C. This is very general picture. It happens everywhere. Mathematicians can prove something about that. It's very easy to obtain on computer. Mathematicians can prove that, yes, these stability islands exist. They also can prove that chaos exists. what no one was able to prove in any map like that this chaotic C is indeed what we see, that it is indeed really large. It's considered to be very high, very complicated problem. No one has any hope it will be proved in a century or so. But this is what happens, we just cannot prove it, okay? We have large chaotic C and elliptic island. And this is, do mathematics about this is very hard. And I consider something a little bit simpler problem which occurs to be simpler. And I will explain what we obtain. Instead of this general picture, I will try to look at a very delicate picture. I will try to look at a detailed picture of this. And this detailed picture can be a little bit understood better, more rigorously than this general picture, okay? And if you look more detailed, you notice that inside the elliptic island, you see you have this, again, you have very small chaotic C. So some orbits inside the elliptic island, they don't want to behave quasi-periodically, they behave chaotically, you see? And for example, these points, or points like that, if you start to iterate them, they first behave chaotically, but then they return. And if you look at the return map, this return map just will show you these curves, they show you stability island. So everywhere, this can be proven that almost everywhere inside chaotic C, you must have the elliptic islands. So the situation is that, and then you repeat, inside elliptic islands you have chaotic C, inside chaos you have islands, etc., and so up to infinity. So the picture is like that. So you look at a certain time scale and you see certain behavior, for example, chaotic behavior. But then you notice that on some time scale that if you ignore what happens in between, that you notice that you somehow repeat more or less quasi-periodically. Then you look at a longer time scale, and then you again see that you have certain fluctuations of this quasi-periodic behavior, and again chaos, and so on. So on different time scales, you have different dynamics. And this phenomena of multitude of time scales somehow can be understood, and that's what I want to tell you. And to understand it, one needs this construction. So this is exactly the construction. You take some small piece of my phase space, and you start to iterate it. Some small disk, and you can see the images. And you iterate long time. And then you say, well, I want to see how return map behaves on this image. But my disk is very small, so I want to zoom it. So I want to make it large. So I introduce some scaling map, this C-1, which scales this small disk to a large disk. So I have some disk of standard size 1, and what I do, I just squash it. I make it very small. I just multiply it to some constant. I just make it very small. I put it somewhere in phase space. Then I iterate many times, and then I scale it back, and see the result. And the result is called renormalized iterations, and you can put it at different places. You can iterate a different number of times. And also this scaling map, which make it smaller or larger, can be chosen differently. It can be linear scaling, can be nonlinear scaling. So there is a lot of freedom. So you start with one map, and as a result, you get many maps obtained by this procedure. And then the question is, and this set of maps somehow describes, encodes behavior of your system on all possible time scales, because time scale is given by this number n, and this is it can be anything, okay? For some maps, this resulting set of maps is very small, actually. These are so-called self-similar maps, which shows you the same behavior on all time scales. But my question is it possible to have a map for which this result, after all scalings, you will get everything? Is it possible to have a universal map? This CK is a technical thing, but it's important because, I mean, the proofs are completely different for k equal 1. Large k is more difficult to prove and give you better quality of approximation, okay? So all the results are for large k, so you may forget about this. So the map is called universal if its behavior on all possible time scales contains the whole universe, contains everything, okay? Approximate all possible dynamics. So you take a single map, you rescale it, you iterate, rescale it, and you get everything, okay? Is it possible to have such maps? Such universal maps, and the answer is, it's not just possible, it's always. So it's much worse than possible, okay? So it says that, again, this K is important, but it's technicality. Typical map is actually universal. A typical symplectic map. So unless you prepare it very specially, unless you make some very important symmetries or some special symmetries, your typical map will be will contain the whole, will contain everything. If you look at all possible timescale, it will show you ultimate richness of behavior. Okay. I want to be a little bit more specific. So I want to say, so the game is like that. You give me two maps, map G and map F. This is my target G, this is F, what I have. And the game is what I say that I can always just a little bit tune my map F, just change parameters very, very, very small, then iterate it for a very long time at some place. So I look at the behavior on some very long time scale. And the result will approximate my target map with as good precision as I want. So that's the game, and the answer is yes, this game has a solution. And the meaning of it is that, okay, as I say, symplectic maps is just something which appears when we study Hamiltonian system. Hamiltonian systems we study to describe physical situation. And the meaning of that in any physical situation, you take any Hamiltonian system, if it's typical, unless it's something, unless it has some very special structure. So typically it's not. If it is typical, then on a very, very long time scales, you will see everything. You will see the whole world, okay? So you take any system, you look at a very long time behavior, if you just zoom it and look carefully, you will see everything. You will see the whole universe. And this is, how to say, this is not a result to be proud of, actually, because okay, my job as a researcher is to study dynamics of dynamical systems, to understand dynamics of the system. And this theorem say, well, that I will fail at every instance. Every time I will have a dynamical system and I want to understand its behavior, I will fail. And not just me, everyone will fail. Why? No, it's not funny at all. So I really feel pain when I talk about it. Again, so I can understand something. I can work hard and I can understand a lot, but I will never be able to understand completely any given system. Not maybe some system can be understood, but these systems are not typical. Okay, typical system is beyond human understanding, and and the question is how to make it. At least to me, I cannot live with that. I don't like it. My question is how to make it useful, how to make it applicable, how to twist it in order to make it applicable in the real world, and this is my idea. This is how I want to make it applicable. And the point is that you should not take it as a philosophical statement, because as a philosophical statement is just very cheap. No, I mean, no, I didn't want. Okay, look. I mean, it's very easy. You do a serious face or enlightened face and say something like that. It costs nothing. Okay. The point which I want to make is that this nonsense, it's nonsense, but this nonsense can be formulated rigorously as a mathematical theorem. So that's important for me, okay? And so, for example, what's written here? You assume, so what's the logic of that? You assume that reality exists. What does it mean? You assume that what you see is actually a trajectory of some Hamiltonian system, or iterations of some symplectic map. This is your assumption. Then you just do, then the reality, when it exists in an illusionary form. The Hamiltonian which you can choose to approximate your observation can be taken arbitrarily. So, and all these illusions are equivalent, so there is no difference between them. Okay? And it's not just a theorem, which, first of all, it's proven. And the point is that it's kind of a general theorem. And every time I see a general mathematical theorem, I also get suspected. Maybe it's just a game of trivialities. Maybe just, definitions are twiddle so it sounds general, but it's just interchanging symbols. But no, it's not, at least to my understanding, this is not a trivial proof. So it's not super complicated, but it contains non-trivial computations, which I will show you. So it's a decent mathematical theorem. And this is what's interesting to me. And what's important to me, that it's not just a theorem. The proof is actually algorithmic. It's actually a precise set of instructions. So you are given your reality, your set of observations. You are given your illusion, your set of physical principles from which you build your Hamiltonian. And there is a precise set of instructions how to match your reality to your illusion, how to do it. Okay? And this is this is the set. This is basically this cooking recipe. So it's the same game. You have a map G, map F. You want to match map F to G. And this is exactly steps to do, exactly like this cooking book. You follow the recipe. You do step 1, do it properly, do step 2 properly, and so on. At the end, you will get a result if you do everything properly. And if you look at this, then what you will see. It doesn't mean what it, I mean, of course you cannot verify it just by looking at that. So keywords are this first return map. First return maps means that I iterate my map very long time, and then I look at the result, at the return, which means that I ignore certain time scale, and so when every time it's written here, first return map, it's here and also somewhere here, and so, and also here. Every time it's written here that I take first return map, it means that I go to a longer time scale, okay? Also what I do perturbations, which means that I tune parameters on my map. See, make the frequencies commensurably. I change frequencies a little bit. Also cut the terms, which means that I threw away some terms. I change some parameters on my map. And perturb the identity map. It's change of parameters. So there are many steps, and what I do on the steps, I either change parameters in a prescribed way, or I go to certain prescribed time scale. And what I also do here, and I also do coordinate transformation. So this bring the map to normal form, it's a coordinate transformation. And there are others. Rescale is also coordinate transformation. So I do these things. I tune parameters, I go to longer time scales, and I do coordinate transformation. I choose coordinates in some way. And this is non-trivial, this last step is non-trivial because you see, I always say map, here I say diffeomorphism, because for maps no one knows the proof that it's possible, but for diffeomorphism one can prove it, again, in several steps by making looking for long time scales, by making coordinate transformation, by making some tuning of parameters and so on. So I just repeat, why it's important to me to say that there is a theorem which says that any observation can be actually matched to any set of physical principle, any equation with this Hamiltonian structure, and this can be done algorithmically. And since it can be done algorithmically, you may try to do physics like that. Computer can do it, okay? So. And of course, I mean, I don't believe the physicists just, now we have this theorem, we have this algorithm, so can we replace all physicists by robots? I think not, because it's not how science is done. So it's only in theory that we can choose coordinate, we can work in our system in any coordinates we want. It's not true. Because in reality, there are well-studied situations, studied by people before us, who found the appropriate set of physical principles to describe the observations in a concise way. They found good coordinates in which this picture becomes easily understandable. And we have absolutely no right to choose different coordinates in these situations, because I mean, it will be antisocial. No, it's really, because I mean, science is not like you just negate everything which was before, you just put new theory. No, you should really build on existence theory, just somehow made little small changes. So it's not what we do. And the point is that, so of course nobody is doing physics like I propose, and I'm sure in the future it will not be done like that. Still, there are some situations where we really don't have a clue. And in these situations, maybe this theorem can be helpful, because it really says that you should not really think much about which Hamiltonian to choose. What you should think about how to match your Hamiltonian to observation. So this is and there are situations where we really don't have any physics at all, any previous physics. So we have observations which we cannot interpret, which we don't know, and then we are absolutely free in choosing. So this theorem somehow reinforces the idea that we can choose any Hamiltonian we want. And we have a good chance to get a good physical theory out of that. And I want to give you an example how this principle can indeed help. And of course, I will not follow this cooking book because it's, I mean, it's always stupid to follow prescription. So it's one should just do what's right. And it is again situation where so far, at least I'm not aware. It looks like it's a problem which exists for 90 years by now. It's not like many people interested, but it exists, and it has absolutely no explanation. I mean, when I say absolutely no, I mean that I don't know. Maybe somebody knows. And I don't know that this explanation exists. And it looks like that just knowing this fact, that basically a typical system can show you all type of statistics, all type of chaotic behavior which is only possible. Just knowing this fact can actually give a new insight to this old problem. And this problem goes to this 1925. This was the paper where it was discovered by Johnson. He was working in Bell Laboratories. He was studying vacuum tubes, noise in vacuum tubes. He was measuring, and this is from his paper, he was measuring noise in vacuum tubes. And what he noticed that the amplitude of this noise, power, so there is noisy signal, you look at power at certain frequency range, and the power, if frequency goes to become smaller, the power starts growing. And if you look at this picture, so this is his picture, his experiments. And he studied several tubes and more or less similar pictures. And so you see, his frequency is 100, he is 10. And here the result is like somewhere around 1. And when you have 10, it's somewhere around 10. So your frequency decreases 10 times. So this magnitude decreases 10 times. So your noise is inverse, approximately, with the accuracy of these measurements, is inverse proportional to the frequency. Okay? So he noticed this fact, and he also noticed at that time there was some theories, and he said that this picture cannot be explained by the existing theories. And he published the paper. And as I understand, so far, so it was 90 years ago, this picture is still not explained by any existing theory. Okay? And which is okay, but it's actually, the situation now is much worse because people did more experiments somewhere in the 60s when they start to study semiconductor devices. And it actually, the effect which Johnson discovered in this particular vacuum tubes is actually everywhere. Every time you measure current, electric current, so you have some sample, you have particles going in, charge carriers going in, charge carrier going out. So it takes some time for a particle to stay in this sample. So you compute electric current. Basically, not a computer, you measure electric current. And this is a charge times velocity times number of particles. So it's a current of each particle times the number of particles. And it has some mean value always, so it's some average value. And it also fluctuates a little bit, so you have fluctuations. And if you look at these fluctuations long enough, then you see this picture everywhere. And this is a problem because why it's everywhere? So it's certain universal phenomena for which maybe in particular situation people have some theories, but there is no universal, so it's a universal phenomenon for which we have no universal explanation at all. And what's written here? So this omega is a frequency. So we have fluctuations. And some fluctuations are very fast, but some fluctuations are slow, so they just grow, and then so you just change your average a little bit, and you stay there. And so each fluctuations have certain lifetime or correlation time, and this omega is inverse to the correlation time. And you measure how many, what is the power in the fluctuations for a given correlation time, and you notice that this power is inverse proportional to this omega. It's not very accurate because it's experiment, it's solid state experiment. So you have a point. These points are experimental points, but these points more or less accurately go along this curve, which was first discovered by Johnson, this inverse proportionality. And the problem with this curve is it flatly contradicts to statistical physics. Statistical physics predicts a certain power, certain saturation at very small frequencies. And it's also impossible. It just contradicts to mathematics. There is a mathematical theorem, which is a very simple theorem, which says that no matter which signal you measure, it really absolutely doesn't matter which signal. Physics is not important here. Any signal you measure, if you compute spectrum, a power spectrum fluctuation, and draw the graph, the area under this curve must be finite. But here, if you take this integral d omega omega, this integral is infinite. Okay? So this formula just cannot be. It's just effect of inaccuracy of our observation. The problem is that this formula is very well established, so the best experiments, they run for, so people measure for 3 months. So they take a sample, took current through it, somehow isolate from outside world, I don't know. It was somewhere inside 75, there was this experiment. And for 3 months, they measured the signal. The function j is a function of time. How they do it, it's unbelievable. So if you imagine the amount of data they should take and the amount of accuracy they should, and what they did it, and they still see for 3 months of very low frequencies, like 1 or 3 months, they still have this law approximately. And so they see it, it's just impossible. So the solution is that if instead of 1 here you put, say, 1 minus epsilon, then this integral will be finite. So the idea is that, of course, we cannot contradict the mathematical theory. Of course, we don't have 1 over omega, but we just very close to it. So we somehow on the border of possible. Okay. So that's the interpretation. We have a noise, and this noise is on the border of possible. Okay. In principle, mathematically possible. So why it's true? And I will try to propose my explanation. It will be very short. So this is an object. J is a product of two free quantities. So the question is, so we have noise here. So this noise is created by noise in one of these quantities. You can think about noise in electron charge. Electron charge is fundamental constant. So maybe our universe is such that we have noise. I don't consider this. So, okay. But it's a legitimate question. So maybe we have certain vacuum fluctuations with the spectrum. And this is a particle speed. Maybe particle speed has this fluctuation. So we assume that it's not. Okay. And so maybe this number of particles inside this sample is a function of time, because some particles may spend longer time. They may get captured by some traps inside. I don't know. So this number of particles inside the sample may fluctuate, so maybe it fluctuates. Then if you look at this formula, you get this formula for number of particles. And so you just, so the question is it possible? Okay, and the answer is yes, I will show you why it's possible, and it's not just possible, it's what must be. And the one thing to say before we continue is that, you see, I have square here, but not square here. If all the particles fluctuate somehow, if they know about each other, if they fluctuate synchronously, we will have square here. And everyone who studied this law of large numbers or this Gauss central limit theorem recognize that I have square here, I have 1. It means that the particles fluctuate independently. So each particle lives by itself. Okay? So at least it's the best assumption. When you see that 2 here, 1 here, you should assume, well, maybe each particle fluctuates separately. And then, under this assumption, it can be just, this formula can be given a sense. And of course, the true physics of that should be quantum mechanical. But as I said, we are in 19th century, we don't know quantum mechanics. So we think about our particles is just, particles just going inside. So we have a sample, we just push particle inside, the particles go outside, and we measure how many particles will accumulate in the sample. And sample is some crystal, so I have my particle, and it moves inside the crystal. Somehow there is atoms in the crystal create certain potential. So my particle in some complicated potential somehow try to get from here to here. And so it's a Hamiltonian system. So my particle is actually iterated by some symplectic map. So I have my phase space. I have some place in my phase space which correspond particle goes in. And they don't interact with each other because it's somehow my axiom. And some set where the particles go out. And I see my particle gets somewhere in chaotic set. So it just travel chaotically. It may somehow get trapped around the island. So it spends some time. And then eventually it must go out. And if I put particles in my phase space with a constant speed, there will be some random, some quantity, the number of particles which get in, but they did not have time to get out. So there will be some number of particles as a function of time. And I try to compute the average number of particles. And there is a theorem, very simple theory, it's called Poincare recurrence theorem, which basically says you that this number of particles is always finite, no matter which map you consider. But what you may do with some work, you may construct by some quite exotic construction that for every epsilon, there exists some particular symplectic map, not some very special symplectic map, such that this number of particles to some power larger than 1, so it's a little bit larger, on average is infinite. Okay? You can do it for every epsilon, you have different exotic maps. Then you look at the typical map, which is not exotic, it's typical. But you know that we have this theorem that it is universal, which means that whatever exotic phenomena happens in any exotic map, it also happens in this universal map simultaneously. So in this map, which is typical, so every map, unless you have a very pure crystal, so unless you have some very orderly system, if you just take typical system, real-world system, it must be universal. So it must show all possible types of exotic behavior. In particular, for all epsilon, you have this property, this average value n to the 1 plus epsilon, and then it's just simple computation that fluctuations of the number of particles, the n capital is the number of iterations you need to get from here to here. I forgot to spell it. And then this number of particles behave exactly like 1 over omega, 1 minus epsilon for any epsilon. So it's exactly the formula which we look like. So this is a solution, you see. So we have universal phenomenon. We have universal observation from real world with a current in a different conductors or semiconductors. And then we say that the same statistics, and we know that this universal phenomenon is that we are always on the border of possible. And the same statistics you obtain if you just look at universal maps. Why? Because universal maps are also on the border of possible. If you wait sufficiently long, you will see everything, which is possible. So you will push yourself on the border of possible. So this is a, I don't know how, 5-minute solution for a very old problem. And I don't like it. Why? Because what did I learn from it? I learned nothing. Okay? What I learned? I just learned that when I see this 1 over omega noise, I should not be surprised. Okay? Why? Because a typical system should show it to me. And this is the problem with this result, and this is really kind of disturbing because this is conclusion. What I want to say that not just in general, but in a typical, so it means practically every Hamiltonian system, chaotic behavior is so rich and so diverse if you look at a very, very long time scale, then you just cannot get information from it. So when we do research, we want information, but you look at the system, you look at this chaos, and there is no way to get, you know that it's unbelievably rich. It's beyond everything possible, beyond human comprehension. You know it. So you look at the system, and what information you get? Yes, you get this information that is beyond human comprehension. So some problems, they become unsolvable or just difficult, so I want to understand the system. No, it's unsolvable. Some problems like that, they become trivial, so just, well. But in both cases, we don't get information, and that's the end of the story. No, I didn't. I wanted to say that it's a depressing result. It's not something to laugh at, so this is a mistake. So this is not fifth floor. It's exactly the place where we started, senior common room. It's somewhere over there. It's on the, okay, we will show you. So we will have drinks, and that's it, okay.
Well, thank you very much, Dima, for this enlightening and encouraging talk. We can all go home and feel good about ourselves somehow. Maybe there's some questions or comments from the audience. Yep.
Should you be surprised if you see a system that doesn't have 1 over omega?
Yes. No, the answer is, the point is, this is again, this is not a theorem which is, it says that in principle, if you wait very, very, very long, then you should have this 1 over omega spectrum. But, so I don't see it. Maybe I don't wait sufficiently long, you see. And also it depends which system you study, because if you do it in a computer, usually your system depends on finitely many parameters. And here, I will show you. Here, for each epsilon, to achieve this, for each epsilon, you need certain parameters. So you need to push your system it's a small tuning of parameters, but you need to do it. So you need one parameter to push your system for this epsilon, another parameter to another epsilon. So to achieve this for every epsilon, you need infinitely many parameters. So if you work with if you take a map, start to iterate on a computer, you will not see these statistics at all because you don't have enough parameters. If you take a real-world system, then it has probably infinitely many parameters by itself. Then if it's typical in this sense, then you... Okay. So you see the difference. It's okay? Okay.
Any more questions, comments, maybe? Yeah.
I cannot. They are not just universal, they are typical, they are infinite. Non-universal map.
Exceptional ones.
Yeah, it's also infinite, yeah, sure. There are so-called hyperbolic maps, they have hyperbolic structure, and they are not universal, they are really, yeah, so it's also a large set, just, yeah. Okay. Yes, it's infinite.
Any other questions or comments?
Okay, so you had a proof which was containing 8 items. If you decide to write this proof down rigorously, how long will it take?
I don't know, 20 pages, something like that. No, it's not long. It's 20 pages, something like that. Yeah.
Any other question? No? I think actually Tima's talk excellently shows how important it is to ask the right questions or to find the right questions. Yeah. Maybe the question of what happens when time goes to infinity is not really the right question, or maybe this leads to trivialities or something else. And for typical systems, so this is, I think, a very interesting development. Of course, when we understand dynamics, the classical question is like, what happens when time goes to infinity, and can we describe this in typical systems? And I would say that what I get from Dima's talk is that maybe this was not exactly the question one should ask if you want to understand what happens in reality in some of the things we want to know somehow.
I don't understand which question one should ask. That's the.
Okay.
I really don't understand, so that's the answer. So.
Okay, well, we will have lots of time, hopefully, to discuss that further. Thanks for everyone for your attention. And we meet each other over drinks in the senior common room. Thank you very much.